This is the 52nd episode of the Quant University guest lecture series. And today we are very fortunate to have Dr.Agus Sudjianto from Wells Fargo. He's going to be talking about his research on beyond explainability of machine learning models. So welcome everyone again. So this is the last but one session for the year. So we've been having multiple sessions in the spring, in the summer, and in the fall, we have been having many sessions. And today we are going to be talking primarily about what does this whole notion of explainability and interpretability mean whenever you're talking about different kinds of pragmatic applications in the financial industry. So Agus and I, we have been discussing these themes for many, many years now. And he and I, we have been organizing a cohort of industry practitioners to talk about AI risk management. And we're looking at various facets, and interpretability and explainability is very much of interest, as financial models are no longer just stochastic statistical models, and we are building a lot of data-driven and machine learning processes to kind of factor in all the new innovations which are happening. So I thought it's contextual for us to have this discussion to make sure that we are not kind of lost in the possibilities and the theoretical possibilities of what explainability means, but also looking at it from a pragmatic sense of what does it actually offer and how do you actually factor that in when you have various constraints, especially in the financial services setting. So welcome, Agus. It's always a pleasure to have a discussion with you. And a brief introduction, Dr. Agus Sudjianto. So he's had multiple positions at Bank of America, Lloyd, and he currently is the Executive Vice President, and he leads corporate model risk at Wells Fargo. And I'm pretty sure everyone here is aware of Agus's work. He's a prolific writer. He has participated in multiple discussions, and he is a really sought-out speaker. And also, I don't know how he finds time. So he's into hiking, and he's an avid traveler. And I'm just sure, Agus, that you somehow can manage like 24 hours in addition to the 24 hours you have in a day to kind of just put everything together. So it's always a pleasure to have you. And Dr. Agus has an engineering background, and he and I, we sometimes have discussion about our mechanical engineering past. Agus had positions at Ford, and also he has a doctorate degree from Massachusetts Institute of Technology. So welcome, Agus, and I will stop sharing, and I will let you lead the discussion.
Thank you, Sri. Thank you so much for the time. It's always a pleasure to have a chance to talk to people in this area to learn something new as well. So you have done a terrific job having a series of speaker in your session. I follow some of them. So thank you for all the work that you have done. So today, what I would like to do is sharing my thought. This is a personal thought as well as some of the practical work that we do at Wells Fargo as well. I'm trying to make it as interactive as possible. So if you have questions, put it in the Q&A, and Sri will help you to help me to ask questions along the way. So feel free to interrupt when appropriate, Sri, so that we can be somewhat interactive. Let me start sharing my screen. I hope you can see my screen.
Yes, we can see you.
Okay. And what I will do is really the specific topic that we talk about today is explainability, but I want to talk to something beyond explainability. Explainable models are important, but we need something more to that. So when we talk about this is part of it, that's my interest working in not in the area of post-hoc explainability, but in the area of how to make sophisticated machine learning model into inherently interpretable model. Some the area developing really fast, and some misconception out there as well that I would like to talk throughout. If we have explainable, we apply explainability tool on top of Blackbox model, we have to be cautious because that doesn't make the model explainable, right? We're just trying to explain the model. We're trying to explain the Blackbox model using post-hoc explainability. It doesn't make the model itself explainable. So that's we need to keep in mind in perspective. And when we look at inherently interpretable model, some misconception out there as well that interpretable model will be simple model, will be either shallow decision tree or linear regression. That's not true. We can make sophisticated machine learning into inherently interpretable model. And there are something that we can do, and we'll share a little bit about my thought and my view how to do it. And there are a lot of benefit dealing with inherently interpretable model beyond just explaining the model, beyond just understanding the model, but really to understand really the conceptual soundness of the model, dealing with the how to do model diagnostic, have the certified or comprehensive understanding of the model weakness, etc. So that's what we're going to talk about beyond just simply explainability. Let's see. Okay, a few topics that I want to talk about. We'll touch a little bit about machine learning application banking very briefly, and machine learning risk. So just I'm not going to delve into great detail, that itself can be a separate topic, but I just want to touch a little bit because that will set the tone or set the need for interpretable model. We'll touch about explainable AI, XAI, and some promise and some pitfall in that area. So as a user, we need to be aware about that. Then we talk about beyond explainability, inherently interpretable machine learning model, and how we do that, and why it's important. What do we get out of it? When we talk about this, people often think misconception as well that neural network is a black box model. Well, we can make neural network specific class of neural network as very, very interpretable model. And even deep ReLU network, we can make it interpretable model. So we're going to talk about that. And if we have time, at the end, I want to touch the area called adverse action reason code. This is really explainability to end customer for credit underwriting. When customer get declined, we have to explain why is that and how interpretable model lend itself to facilitate that if we have time. If not, we'll let's see how it goes. Okay. All right. Touch very quickly in application in banking. Typically, when we do application on machine learning in banking, it really two stream. One is for predictive analytics. This is mainly dealing with structured or tabular data, and there's a wide of traditional, very broad traditional application of that. That's very, very obvious, like for credit risk, market risk, fraud, etc. So very, very straightforward area that traditionally done using statistical model, simpler statistical model. We can do machine learning. That's very, very somewhat no-brainer and easy to do. And the question is, how can we do it safely, right, using machine learning? And then the other stream is really dealing with process automation. This is mainly dealing with unstructured data, be it voice or language, right? Natural language processing. Bank is very, very process heavy, so lend itself to automation. So here we can apply machine learning, particularly natural language processing, to many, many different area, conduct surveillance, customer support, etc. So that's really broad based. Banks typically don't do much with video or image. So, but we do a lot with the natural language processing. Model risk, touch a little bit because that set up the tone why we need interpretable model. I believe that all models are wrong. When they are wrong, they can create harms to either the user or the people who use the model or people that subjected to the model. And model wrong can be from model design. It can be from improper model use. The model probably all right, but we know all models have weakness, and improper model use can be can be cause of that, you know. And back in 2008, financial crisis is part of it because of improper model use as well. The infamous Gaussian copula, and then in a month or so ago, the problem that Netflix had, the Zillow has, right? The Zillow problem is somewhat of the improper model use as well, can be viewed that way. But a lot of chatter out there, a lot of news every day. You look at it in terms of a model that can go wrong, and then they're wrong. They can create problem from privacy, ethical, discrimination, safety, on and on and on. From very complicated model, probably like self-driving. In the news today, when I look at my Apple News this morning, Pony.ai, self-driving in California, California revoked the license to test because they have accident. To all the way model that sounds very mundane, like recommender system, right? So Netflix has a lawsuit pending. Their recommender system is accused to kills people, right? Because recommending movie that's very, very harmful. So a lot of situation that we have to be careful. And in the case of improper model use, I would argue that inherently interpretable model is very important for that. So we'll talk about that a little bit more later. So when we start talking about AI or ML, there are amplified model risks. From the data side, dealing with privacy, suitability, bias proxy, on and on, right? And then from modeling side, dealing with large number of correlated variables, then opaque or black box modeling framework. So talking about transparency, interpretability, talking about identifiability of model, talking about causality and stability of model, fairness, and etc. And then the use of a lot of algorithm-driven, people typically do algorithm-driven or parameter estimation, like AutoML, right? So problem with data splitting of training and testing, and hyperparameter choice, overfitting and robustness is a rampant problem in machine learning that we have to deal with, and incorporation of constraint and so on. And then the language model, the transfer learning, the multi-model language, you know, the large language model that used to adopt it to be used for specific applications. So a lot of amplified risk on the modeling perspective, and then on the operation when talking about change control, how we do monitor data and model drift, you know, the both the covariate and concept drift, and of course security, because it's when we talk about machine learning model, it's really software with ML embedded in it. So any software, of course, you're dealing with security issue. Okay, let's touch about the taxonomy that's setting up. I'm going, among all those risks, I'm going to focus on the transparency and interpretability today. We can talk about another time, talk about subject in terms of causality and stability and robustness of model that itself warrant a lengthy discussion on that subject. But today we'll talk about the focus is on the transparency and explainability. When we talk about explainable machine learning, it's really two main streams, right? One is at the top, intrinsic interpretability, model that inherently interpretable. And then at the bottom, we talk about post-hoc explainability, Blackbox Model, apply to Blackbox Model. So the tool are really model agnostic. I don't care about the model the model is black box. I don't care about what's inside. Let me apply a tool to explain what this model does. So when we talk about explainable AI, when we talk about explainable machine learning, unfortunately, people talk about the bottom side, the post-hoc explainability. And I'm trying to convince you that we need to shift the discussion from that into intrinsic interpretability today and how we do it. You know all this thing in terms of post-hoc explainability as global, local explanation, surrogate model, on and on, LIME, SHAP, variable importance, PDP, ALE, and a wide variety of model of approach in that area. So we'll talk about the weakness of those and why we need the top one whenever possible. With the advancement that we have today, I feel like we are at the juncture when we can design interpretable model from the ground up without sacrificing performance. So that's when we talk about intrinsic interpretability. The traditional model is at the top, logistic regression, shallow decision tree, etc. But we're going to talk about today is really high performance model, constrained architecture of deep neural networks, and so we'll focus on that and how to design inherently interpretable model. I'm not going to touch about this, okay? All of you that's interested in, so a lot of talk, a lot of people talk about the Posthoc Explainer. It's so many out there, and with each producing different result and for different use. So I'll touch when it's really relevant to compare with inherent interpretability today. So black box model with model agnostic explainability, in particular, make it difficult to really talk about conceptual soundness of a model in the world of regulated industry like banking. That we have guidance called XR 11.7 or OCC 11-12. Many of you that's not from banking industry, I highly recommend you to read those. XR 11.7. Very, very good. It's the Bible that we use in the in banking to manage model risk. So very, very good read that you should do if you haven't done so. That's the problem with black box model is the conceptual soundness, something that very, very fundamental required by SR 11.7. Does the model make sense? How do we know the model makes sense? So that's kind of things that we're talking about. And beyond explainability, when I talk about that, we're going to look at later in terms of some example in terms of model diagnostic weakness and verification. Let's say if the model need to be monotonic with certain input variable, we need to make it so and guarantee, right? So that's an important subject. Post-hoc explainer are approximation. At the end of the day, all those SHAP, LIME, all those tools are approximation, simplification of true model. Try to explain the model, right? For example, SHAP or LIME, perturb the data locally, fit the model or calculate and do assessment around it and do the variable importance. It's an approximation. So because it's an approximation, it's not 100% truthful. And because of that, we have to use it with caution and careful, with care. It cannot give false sense of confidence, false sense of security that I have an explainable model. So we have to be very, very careful when we do post-hoc explainer. Black box model, XGBoost, and all of those things can be very, very easily overfit. And with post-hoc explainer, when you apply post-hoc explainer to overfit model, it can be misleading. So I give one article reference here by Chris Molnar. I think you should check. And overfitting issue is sometimes it's easy to detect, right? When you look at your trainings error compared to testing error, the difference is quite wide, that's indication of overfit, right? So model that's that don't overfit, the training error and the testing error should be relatively close. When you have a wide difference between the two, that's indication of overfitting. And when that happens, and this is very easily happen and often happen in XGBoost, right? So when you run XGBoost, you will get a very, very good low training error, and then the testing error will be significantly larger, often order of magnitude larger. So that's is indication of that. When you apply post-hoc explainability, it can be misleading because of that situation, and we'll show some example. There are a few recent articles in that criticize, and I just pick a few of them. Pick one here. In healthcare, the article appear in Lancet Online, talking about the false hope of current approach to explainable artificial intelligence. Basically, talking about the problem with post-hoc explainability. And many of you heard about Zillow, reading Zillow, right? And Zillow themselves touting that they use explainable AI. So explainable AI is not a panacea. It has a lot of problem with this, and we'll talk about that a little bit later and why, when it's needed, that's where this can fail, right? So we'll do some example on that. In particular is this. Let me jump a little bit on that. Model will experience either distribution drift or concept drift, right? The model will not perform as expected under a certain situation. In Zillow case, for the month, during the month where the home price increased very rapidly, the Z estimate is below the price. So Zillow is using the Z estimate to do bidding, right? They use it to bid because they do buy and sell. So the model, they lost the bidding because their bid is lower. So what happened when they lost the bidding? Under a black box model, we need to understand what can we do, because every model may have weakness, will be override. It has human in the loop. If we have human in the loop, we need to make sure that the human can be in the loop appropriately. If human need to override the output, the person need to have information beyond the model. The person need to understand what the model cannot do so that I can do override in a proper way. In banking world, when COVID-19 hit about 2 years ago, a lot of model doesn't work. That's common, right? A lot of model didn't work. So what happened is people do overlay. People put override and overlay. But if the model is explainable, people understand where the weakness coming from, and they can do it appropriately. They can do sensitivity analysis appropriately. For example, because of forbearance, because of loan forbearance, or during the COVID-19, it's actually because people can, if they don't pay, they get forbearance, it cannot impact their credit score. During COVID-19, actually the credit score of people, the FICO score of people going up. And model that use delinquency, people that delinquent in making payment, they will be getting the wrong input, right? Getting the wrong input, because the person should be delinquent, but we cannot flag it delinquent. So the model see it, the person not delinquent. The model see as the person the FICO increase. So we know, if we know the effect of FICO, exactly how the model work, the effect of delinquency, how this thing work, people can make model override appropriately, can do proper sensitivity analysis. And that's the power of interpretable model. Explainable model will not be able, post-hoc explainability will have difficulties to deal with that. So really operating model safer require interpretable model. So let's talk about inherently interpretable model. Okay, unlike post-hoc explainability, we focus on inherently interpretable model. The second bullet point is very important. An inherently interpretable model facilitates gist, intuitiveness to a human, give insightful interpretation. So when model doesn't work, people know what to do with the model. So these things that really important on the inherently interpreted model, providing gist and intuition so that human can make the right decision when they need to be in the loop. The problem today when we talk about interpretability is very loose concept. People define it differently and mean differently. You read different article, lots of article, debate semantically between interpretability and explainability. So I'm not going to go into that. We're going to look at it into something that's very, very practical. At the end of the day, at least at the current time, we don't have quantitative measure of interpretability. It's a qualitative measure. We know it when model is interpretable, and some of you that interested more detail read our article in archive about designing interpretable model. But let me do something in terms of what we meant by interpretability. So when we start designing interpretable machine learning model, we're thinking about two aspects. The feature itself, the features need to be interpretable, and then the architecture of the model itself need to be interpretable. On the features, the feature need to be meaningful. And for tabular data, this is a lot easier because we have variable name. It can be not very easy when the feature have very high interaction. If you combine variable, multiple variable through interaction, even simple plain interaction, it's becoming more difficult to interpret as well. So simple regression model, it has high order interaction. It can be not interpretable too. So we have to start with meaningful features. For unstructured data, it's more complicated because now combination of pixel or combination of word to be meaningful. Okay. And second one is causal feature. The input has clear meaning why it's producing certain outputs. So causal relationship between input and output make it also understandable. Hey, yeah, because of this, the output does, so that makes sense. Okay, looking at the causal feature, and then talking about regularized features. If I throw in model with 400 input, 400 variable or 500 variable or a lot of variable, it's very, very difficult to interpret the model. So somehow we need to regularize it, make it fewer, because human being can digest fewer information. So we need to regularize the features. And then on the architecture side, I would argue if the model is modular, in particular if it's additive, it's understandable. If it's not additive, it's more difficult to understand. So if this is part of it, in the traditional linear regression, I have additive term, it's easy to understand. If I multiplicative term, it's more difficult to interpret. So additivity is somewhat facilitate the understanding. Sparsity, the model need to be sparse. If the model very complex, it's more difficult. We'll go through some few examples of that. Constraint can make it more interpretable as well. If the effect is monotonic, that people can say, yeah, that's monotonic, that makes sense. But not everything is monotonic, of course, right? But when it's applicable, monotonicity improves the interpretability. And then the construction that near orthogonality is also, because then near orthogonality, so you can separate the component. So that help as well if it's applicable. Okay, I talked about this already, the characteristic, additivity, so it can be decomposable, sparsity, need to be sparse. Linear model, linearity, the more linear, expression of linear is easier to understand. The more non-linear is more difficult to understand. So locally, if it's linear, it's easier to understand because we are accustomed to it. Smoothness, the effect is smooth. It's very, it can facilitate a interpretability as well. I talk about monotonicity. Visualization, we can visualize it. I can look at the main effect, the reason of PDP and ALE and eyes. Those are very popular because, hey, I can visualize it. I can look at it in 1D. 2D, 2D, I can still look at it. Higher interaction is more difficult. So how can we visualize the effect? That's very, very useful as well. Projection, particularly sparse, near orthogonal projection, make it easier to interpret. We go into few examples. And then model segmentation. You segment it. If it has a fewer segment, it's easier to understand because people can see why you belong to certain segment, why a certain customer belong to other segment. It can be understandable. If its segment is too many, it's more difficult to understand as well. So that's kind of like qualitative characteristics. How can we make a model, or how we judge model more interpretable or less interpretable? Let me pick one or two examples. This is a generalized linear model. Well, when we talk about interpretability, it's also talk about interpretability locally and then globally. So we try to rate now, which is 1 star to 4 star. This is very easy things to do qualitative measure. Is it additive? Generalized additive model is additive. Sparsity, well, I can make it sparse. So if I do make it sparse, then yeah, that's good. Linearity, yeah, generalized additive model, we can make locally linear. So that can be understandable as well. If it's non-linear, we can still decompose it. Smoothness, we can control it. Monotonicity, we can apply constraint to make generalized additive model. Monotonics, visualization is very easy because main effect only, etc. Decision tree in the same way. Talk about decision tree is really additive, right? Because it's just a piecewise discontinuity in the additivity side. So we look at the you can write decision tree into an algebraic equation based on the variable split that's expressed as indicator variable and has certain value. So but for each node is really additive based on this condition. You can make it sparse, you can control it. Linearity, you can make it locally linear. Globally, it's not, so it's more difficult. Smoothness, that locally you can, globally you cannot. You know, it's because it's not really smooth because of the variable split, right? Locally, I can make a decision tree. For example, I'm using, instead of the traditional decision tree, I can make it an each node linear model, right? So each node, instead of constant, piecewise constant, like the standard tree, I can make it locally linear model. So that's enhanced as well. So let's go to something that's more complex. Here is an example of explainable neural network. Some of you that are interested in can check the paper in IEEE or in archive. Basically, what it does is the input is still just like the input in neural network, but we are going to limit it into much fewer number of input. If I have much fewer number of nodes in the input layer, much fewer number of nodes on the first layer, and then I make the projection, the weight sparse, then I can see that each node really projection. I have a linear equation that is interpretable, and then combine into a univariate. The output of univariate, we can feed it into more complicated neural network to get a non-linearity, but it's univariate. So I can visualize it. I can see it. I can see the effect of linear combination and how the non-linearity, and we can visualize it. You can understand it. So the key is really make the projection layer as few as possible so that we can visualize it, we can understand it, and the meaning of projection as well when you combine it, right? If it's too many, it's will be less interpretable. If it's few, it can be more interpretable. If it's too few, the model though may not perform very well. So it's a design problem that you have to do trade-off between the two. So some of you are interested in You can go deeper on that, follow that paper. Generalized additive model using a neural network. You can do this one both using tree or using network. Actually, there is a tool out there called EBM, Explainable Boosting Machine, by Rich Caruana from Microsoft. That's using tree. I'm using a neural nets here. So either is with whatever your preference, you can do either way. So basically, as you construct, you input individual variable and put it into a network. If you sum it, that's becoming GAM, Generalized Additive Model. It's very, very interpretable. So on the left-hand side, that's very, very interpretable because it's GAM. And then on the right-hand side, I can add now, let's do it two interaction at a time. It's two interaction, combine it into single unit and put it into a network. That will be interpretable as well. At least you can visualize it, how the interaction play a role and how significant is certain interaction. So instead of using fully connected network, you can use, we call it GAMI structure, that will make it interpretable. You can feel free to check the paper as well. It's in pattern recognition, or I think the paper is in archive as well. Here's another example. You can use a single index model 3. You can basically, I'm going still to 3, but at the leaf nodes, I'm going to use more sophisticated model that is fully interpretable. In this case, in this example, we use single model example. So you can make combine 3 with the interpretable model in the node, as long as the 3 is not so deep, the partition is interpretable, and then the model itself locally is interpretable. So that's a few example. Now let's look at we have time to look at the deep ReLU network. I think I talked about this a while back in a previous several sessions ago, maybe a year ago, but I want to bring it again here to see how deep ReLU network we can make it very, very interpretable. We'll go to that example. Okay. So all of you know neural network. I'm not going to go through detail of this, and that's very specific neural network is doing a rectifier linear unit. Basically, it's linear if the value bigger than certain threshold is 0 if not. So that ReLU combination of ReLU creating overall non-linear, but for each sample it's linear, and we'll go to that example a little bit. This is an example that I think I discussed this in previous session that we have, if you follow, but for the sake of this, let me go through this a little bit, and this is important on the diagnostic interpretability. We'll go through that a bit more detail. I'll just do the 2 nodes here. Okay, I have a very, very small, very simple network, 2 layers. The first layer is only 2 nodes. So if I have 2 nodes based on the input, one node can be on, the other node can be off, or vice versa, or both on, both off. Those are basically partition the input space into 4 regions. Both are on, both are off, one on, one off, right? And then based on that, go to the next layer, it partition even further. So partition even further is more detailed. So it's like when you do boosting, it has the same effect, right? You cut it into 3 and then you boost it, you slice it into small things. So it's the same thing. What deep learning does, very, very similar. It's basically slicing the input space into smaller and smaller region. The difference with 3, the cut in deep learning is opaque because it's linear combination bigger than such and such, when in 3 is Cartesian. So the shape of cutting, it can be we call it oblique. It can be more complicated. And for each, once it does basically what network do is it partition the input space into smaller, and for each region, for each area, basically is linear model. Because let's say if I have one input, one node is on, that's linear. Another node is on, that's also linear. When you combine it, linear combination of linear, still linear, passed into linear unit, still linear. So every sample in deep learning, they generate into simple linear model. It's just how, depending on the size of the network, the number of layers, the number of neurons, it creates so many local linear model, right? It's too many. So that's when, but we can count it. So if you look at the paper that we have in archive and the software that we have, that you can try it. It's in public domain. You can try it. It's basically, after, if you run the tool, you can really tracing all those input to the network. You can see, you break it into many different regions, and each region you can see how many sample in each region, what is the performance. In this case, classification, you can have local and global AUC. You even know which region that the model is weaker or stronger compared to the other. And that's very important to diagnose the model, where the model weakness and things like that. And especially in real life, when the distribution shift, you know, hey, my model is good because right now my sample is in the area that have high performance. Then my model can degrade very easily. So that's very, very diagnosable in the case of interpretable model like ReLU network when you decompose it. Here is an example. If we apply to a simple 2D classification, in this case, 4 hidden layer, 40 node each, with 4 simple things like this, it generates, in this example, it generates 530 regions. So on the right-hand side, all the local linear model, I have 530 of them. Do I need all of them? It turns out that you do neural networks, 85% of local linear model only have a single instance, only single sample. This is part of it when people talk about deep network, deep learning is very data hungry, because you need to have more data point for each region. If you have too many regions, how can you make the local linear model reliable? You have to have enough sample. If you don't have enough sample, then it's not very reliable. So that's the thing that we want to do, how to control it. Let me give an example. Probably I'm jump around a little bit. This is an example, the chart on the top right? I have so many local linear model. Every circle is local linear model. Yeah, this is the coefficient for this variable. The lesser the number of sample, the vertical is number of sample. When the number of sample equal to 1, the coefficient is all over the place. So I have a lot of region in my neural network that the coefficient are all over the place. The more sample you have, they are more consistent. If you go to vertically, the more it's more consistent. Cluster around green in this case, because I know the general function, the equation should be green. But if you train network blindly, it will have all over the place. So that's something that we need to control. Let me go back to this. So I have the this problem with the 530, 85% only single instance. Of course, 85% of them are not very reliable. So if we look at the AUC, the performance, testing performance, 93%. It looks like, oh, we are happy. We have high performance model. I am done. My job is done. I can deploy this neural network. So it's not like that. We have to be extremely careful. This is why when building machine learning, and this is what SR 11.7 talk about as well, that outcome testing alone is not enough. Outcome testing can be dangerous, give a false sense of confidence. So you need to really understand the model inside. So here I apply post-hoc explainability. So when I apply post-hoc explainability in this example, I apply sharp and line. Okay. So I pick sample around the bottom of the circle and on the side of the circle. If at the bottom of the circle, what variable are important? It's only one variable only, right? The direction to separate is really x2. When I pick the sample on the side of the circle, only variable x1 are important to distinguish. Variable x2, it should not have any contribution. But when we apply post-hoc explainability, here is an example. The true one, I'm applying deep sharp and kernel sharp. And then I apply lime, and then I apply the exact interpretability. The exact interpretability gives you the exact from local linear model. Lime is not bad in this case, but sharp can be all over the place. Yeah, same thing, I pick another area. In this situation, X2 are the important one. Lime is not that bad. Sharp can be all over the place, right? In other situation, all of them may be okay, or some of them have problems. So this is one of the problem with post-hoc explainability. In particular, the problem becoming really, really bad when you have an overfitting model, which, like what I showed before, overfitting model, right? Overfitting model, the performance still okay, but it's overfit. Then you apply sharp, then it will be all over the place, the answer. So that's what we try to think about as we think about interpretable model. How can, in this back to the ReLU, because it's degenerate into linear model, I can plot all the linearity, what is the coefficient, I can see that, I can plot it, I can see the main effect. So a lot of stuff that we can do to diagnose the model. How important is this variable? Is it monotonics and all those things we can check. We can look at the local performance, global performance. The local performance is important to see whether a variation of performance in different regions. So when we want to have a robust model that will work under different situation, under distribution shift, I know exactly how this model will have problem or not, or how to improve it. Monotonicity, I can check because remember the coefficient, I can simply box plot it. I can see if it's crossing plus and minus, is the coefficient plus and minus, is not monotonic. If we need to be monotonic, we can apply constraint and then check it, whether it's monotonic or not. So interpretable model will allow you to do a comprehensive assessment in terms of some of the constraints. Let me do an example. This is where I only have about 6 minutes here. Let me go through this example. This is a very famous Taiwan credit data, right? So we run a deep learning using 40, 40, 40. It turned out this model, compare it, MLP, XGBoost, random forest, and okay, this model is the best. Give me AUC, right? That's a typical Kaggle competition and typical AutoML. Okay, this MLP model is the best. I picked this one. So what happened? So we go detail on the winning DNN. You look at it, a lot of it create more than 19,000 local linear models. And many of those, actually more than 90%, only have single sample. Clearly, many of the, even though it performed well, but this should not be the right model to do. Right? I do a early stopping, I pick the best model, but you cannot just deploy a model that's coming off that. So we need to check. We need to see, and it has a lot of region with one sample only. Clearly, this is not reliable. Let's look at the effect plot. So because we know exactly the local linear model, we can do effect plot, and you can say the variable on the payment from 1 month ago, from 2 months ago, the direction is all over the place. It's increasing, it's decreasing, so it's all over the place. That doesn't make sense. The model conceptually doesn't make sense because it should be in one direction. If the person doesn't pay a month ago, the person doesn't the status of payment 2 months ago, it should be going to the right direction. If the people delinquent in the payment, it should be more default. So this one just out of the box, you plot it, it doesn't make sense, right? So this is what happened. So now let's regularize it. So we can regularize it, apply let's L1 penalty in this case. So we regularize it, apply L1 penalty, and then you can see how the performance, is the performance changed or not when you apply L1 penalty. So horizontal as L1 penalty. So you can look at the performance at certain point, the performance degrade rapidly, the model is not working, right? So we want to stop when the model is still working very well. And the number of local linear model, which is in red, is as small as possible, right? The number of local linear model is as small as possible because if they are small, they have enough sample and they still perform well. That's what you do. So starting from early stopping model that we got from early stopping, then you can apply L1 penalty regularization You can check in the model performance, and you can check the number of local linear model. So yes, the performance is not as good as, it's degrading a little bit, but the result is I have only 5 regions, and this is the region, the number of sample of each region. This is the local AUC for each region. I know where the model is weak, right? Region 4, this one in particular, sample size is small, the not very weak. And when you look at the variable effects, now makes a whole lot of sense. They are consistent. So this is how to make model in this example, control it to make it more interpretable, because now I'm dealing only with 5 linear model and I can plot the coefficient. So I have model with 5 local linear model segmented into 5 region. The deep learning gave me the best 5 region segmentation and give you linear equation for each of those segments. And the model becoming a lot more interpretable, perform very well, and we can explain, we can see in terms of conceptual soundness. Maybe I should stop right there to give enough 1 or 2 question here, Sri.
Thanks so much, Agus. This is excellent, and I'm just soaking up all the new things you've been discussing and new papers. I have a lot of homework to do to kind of go back and look at the actual papers and look at it. So I think there are a couple of questions. So there's a student here, Philip Kim. As a student, I think it would be interesting to attempt to build the models and replicate some of the results. Do you have any recommendations?
For this, it has
Yes.
checked the GitHub. So Sri, because we put all of this in GitHub, the code, the paper, and everything in GitHub. So if you Google interpretable ML, I think you should find the GitHub interpretable ML.
Okay, so I will
interpret ML or something. Yeah. So you can replicate all this. You have the code, you have the data, it has example, it has paper in there.
So I put in the GitHub repo to the Alethea package also on.
It's not only Alethea there, it has Gaminet, the one that I talk about. It has SIM3. It has a lot of stuff that we talk about today all in the GitHub.
Okay, perfect. So I'm just gonna bookmark that, and I'm gonna send out a note to all the registrants. So I had a question with all the discussion with regulations coming up and potential regulations coming up. So how do you think explainability and interpretability should be framed, and what should be expected of every company to follow and make sure that they incorporate this as a part of the process, and how much of it should be let's do it if we have the time or if we have the technical ability. What do you think should be the balance?
I think it really no one size fit all, in my view. It really depends on how critical the model and what is the risk of the model. What is the impact of the model? For high-stake environment, for high-risk environment that has significant impact, particularly impacting customer, impacting people, I would do only interpretable model. So for things that very, very critical for us, credit scoring, right? Credit underwriting. I will not do anything but interpretable model. And we have a lot of tools, okay? And of interpretable model. We can regularize it. It's just harder to do this. We have to be careful. AutoML will not give you interpretable model. You have to go beyond AutoML, right? So that's what it's harder to do. But I think for highly critical area, you need to have interpretable model. For model that's not very, very important now, I'm going to do document grouping and all those things, and it will have human being to review it later. Well, maybe you can do a bit careless, Okay, maybe you can do a conceptual soundness. It's not something that will kill us, for example, right? Or harm user significantly. Then you can do somewhat more post-hoc explainability. And then when you do post-hoc explainability, try different algorithm, try different packets, and use different techniques to compare so that you can get more consistent view, because they are not consistent. Okay, get something more consistent and get the better view. So I think that's my view. So less critical application. Yeah, run. I can say I run XGBoost 3 tab 7 or tab 10 and boost it 1,000 times. Okay, am I going to have trouble? Well, depend on what model do you use. You use it for credit underwriting, you're asking for a recipe for disaster, right? Critical area, you cannot do something like that. I'm going to apply ReLU and simply just apply deep learning. Well, depend on what you want to do. So if you know it, it will be very scary. If you want to use it for self-driving, like a lot of today, dominant thing is self-driving, or you need to make sure the model is safe. So you have to do all those careful unwrapping and interpretability and testing.
Absolutely. And again, this kind of leads to, the favorite word you and we have discussed multiple times, which is context, right? So, yes. Without context, the methods and the technologies we currently have are just methods and technologies, which cannot be really applied to
context and understand how the model will be wrong, right? And exactly. When the model is wrong, human need to be in the loop, and human need to be knowing how to be in the loop. Otherwise, it will be bad. So if some of you that read the Daniel Kahneman books, Noise, right? Yeah, read page 113. Yeah, page 113, Noise book, Daniel Kahneman. Then you can see the breaking leg problem that Daniel Kahneman talk about and how human noisy. That's where you need model that really interpretable so that human can understand it and they can make a better decision.
Absolutely. And again, next week, I'm sharing some of the work we've been doing in the context of safety critical AI in next week's session at 12 o'clock on Tuesday. And that kind of goes back to, how much of maturity do we have so that we can just delegate into systems? Because when I talk to some of my customers, they always ask me, well, I would like to automate many of these things and just delegate it to a system. So that it generates a bunch of reports, and we'll say, okay, we are doing explainability just because the system is generating a bunch of reports and graphs. But it looks like we still have to do a lot of contextualizing, human in the loop, and understanding to make sure that, we are not just kind of, just incorporating it as a process, but also understanding what's actually happening, even though we are not kind of delving into the minutiae of the specifics.
When we talk about human in the loop, we need to start human in the loop from the very beginning, right? Designing model very, very carefully with human operator in mind. That's who's going to use it. This is what the heart of interpretability, right? I'm building model that whoever owns this model going to operate this model know this model is. So I think as we talk about human in the loop, that need to start from the design aspect of the model.
Right. And again, that's one of my concerns too, because many of the frameworks I see always talks about the techniques and the methods, but doesn't talk about why and how it should be applied. And a prescriptive approach, which is generalized at a very high level, which potentially could be applied to various domains, doesn't really provide the context on when and where should we be using. It's just going to be like an index of options.
I think that's a very, very important and what people in the audience here can learn from Zillow as well. The Z estimate at the beginning is used for web listing to attract customers to come to their website and to list their house when they sell the house with Zillow, and they make money out of that. So if that's the context of use to attract people, need to put the price higher, right? Lower price, people will not be interested in. They want to list it in the area and things that willing to list higher price, reasonably higher price. Now, if you want to use it for buy and sell, the same model, but the context is totally different. Now I need to make profit. I need to buy low, sell high. Can I use the same model for bidding? Then Zillow decided to use the same model, right? The Z estimate. I'm assuming that it is the same model. I don't know if they have different models, just they keep calling it Z estimate. But if it's the same model, even though exactly the same model, the context is very, very different. The model risks are totally different. The way you test it are totally different.
Absolutely, absolutely. And again, this is becoming more and more of concern as we are seeing, the proliferation of, fintech opportunities and buy now, pay later, and various other business models which are coming up, and most of them are, leveraging technology and machine learning. And if we don't really understand the risks of what could potentially happen, we are just basically, generating stories for the media, I guess, with failures, which should not be happening in the first place. So thanks again, Agus. I know we have a couple more questions.
I have to, my apology, I have to jump off. So
we are running out of time.
Email, I can follow up with the question. I'll try to answer it. Okay, Sri,
Absolutely.
Thank you very much. Thank you, everybody.
Thank you so much. And again, Agus will share the presentation and the questions with you later. And for the audience, the next week is going to be the last session. It's going to be between 12 and 1. We'll talk about safety critical AI. And also we are coming up with a course on explainability and interpretability specifically for financial applications in 2022. And the details of it will be available in the Quant University Spring School, which we are gearing up for. And I look forward to continuing the discussion with you online. And we will see you again next week. Thanks again, Agus, for the wonderful discussion, and we'll connect later. Thank you.
Thank you.